As concern mounts among scientists and astronomy enthusiasts regarding Pluto's potential interaction with Neptune, prominent experts like Neil deGrasse Tyson and Michio Kaku have voiced serious concerns about what such a celestial encounter might entail. But what led Pluto to be potentially aligned with a path that could intersect its distant planetary counterpart? And what implications could such a cosmic collision carry for our existence here on Earth? Let's delve into this evolving scenario. Once categorized unequivocally as a full-fledged planet, Pluto was later reclassified as a dwarf planet due to its eccentric trajectory. Nonetheless, this redefinition hasn't diminished its allure, continuing to captivate astronomers and stargazers. Recent predictions from notable academics highlight a troubling proximity between the orbits of Pluto and Neptune. These same experts have issued warnings about the plausible scenario of an impact between the two celestial bodies, which could pose a noteworthy threat to Earth. Pluto's journey around the Sun is characterized by some of the most distinct traits in the solar system. Its orbital period spans approximately 248 Earth years, and since its discovery back in 1930, it hasn't yet completed a single full rotation around the Sun. One of the most captivating aspects of Pluto's orbit is its pronounced elliptical shape, deviating significantly from the more circular trajectories followed by the primary planets. Additionally, Pluto's orbital inclination sits at a steep 17 degrees relative to the ecliptic, making its path far more extreme than those of other planets. A particularly significant feature of Pluto's route is the point at which it intersects Neptune's orbit. For nearly 2 decades within each revolution, Pluto travels closer to the Sun than Neptune does, defying expectations based solely on their positions in the solar system. Why, then, has a collision not already occurred between the two? The answer lies within the gravitational pull exerted by other planets. Analysis of Pluto's orbit began shortly after its identification, presenting a mysterious path for astronomers to interpret. Unlike most planets, which orbit in a more aligned manner with the ecliptic plane, Pluto stands out due to its sharply inclined and elliptically distorted trajectory. The intrigue deepened once it was understood that Pluto's orbit actually crosses Neptune's. Despite these complications, Pluto's orbital stability serves as a testament to the complex workings of gravitational interactions in space. The three-body problem in orbital mechanics involves understanding the movement and gravitational effects among 3 massive objects. In this context, Pluto, Neptune, and the Sun. This problem elucidates the intricate gravitational choreography that determines how their paths evolve over time. Concepts like asynchronous libration, nodal libration, and the so-called VZK oscillation provide insight into this astronomical puzzle. Scientists assert that asynchronous libration, which plays a crucial role in maintaining orbital balance, ensures that whenever Pluto's path intersects Neptune's, their spatial positions are offset by at least 90 degrees. This misalignment is vital in preventing direct collisions. Nodal libration offers another layer of protection by ensuring Pluto is positioned either significantly above or below Neptune's orbital plane during close encounters. The VZK oscillation explains why Pluto's orbit appears erratic but remains remarkably consistent over vast time spans, even though it might look unstable. Simulations from the late 1980s demonstrated that Pluto's trajectory is indeed chaotic. Minor initial shifts can result in vast differences over geological epochs. However, these same simulations also revealed that Pluto's orbit remains predictably stable over billions of years. Advancements in computational modeling have deepened our understanding of how massive planets such as Jupiter, Saturn, and Neptune influence Pluto's trajectory. Particularly important is the unique resonance between Pluto and Neptune. For every 2 orbits Pluto completes, Neptune finishes 3, which adds a layer of orbital protection. Jupiter's immense gravity plays a pivotal role as well, exerting a powerful stabilizing influence. Saturn, though less dominant, also contributes to this delicate gravitational dance. Meticulous simulations have confirmed that the combined effects of these planetary giants secure Pluto's path through space, ensuring long-term predictability and minimizing chaos. These interplays are essential in preserving the orderly motion of bodies in our solar system. Without such mechanisms, the solar system would descend into a far more chaotic state, possibly leading to increased risks of planetary collisions or the ejection of celestial objects from stable orbits, with ripple effects throughout the system. Understanding Pluto's orbital characteristics is especially important given the debate over whether it might eventually collide with Neptune. This awareness offers a clearer view into the dynamic and intricate behavior of the solar system. Pluto's case illustrates how orbits that seem unstable can attain equilibrium thanks to the precise interactions of gravity and celestial motion. Continual monitoring and analysis of these mechanics are vital for enhancing our comprehension of our cosmic environment. Exploring the deeper mechanics of space frequently reveals the unpredictable and often quirky behavior of celestial bodies, and Pluto's unique orbit is a prime example of such unpredictability. The concept of orbital chaos vividly demonstrates how a celestial body's trajectory is sensitive to its initial velocity and position. In Pluto's case, even small variations can dramatically reshape its long-term path. Computer modeling has been critical in helping scientists better grasp Pluto's motion. By tweaking inputs and simulations, researchers can observe how minor differences ripple out to substantial changes in orbital direction. Studies from the 1980s revealed an intriguing aspect of Pluto's behavior. Despite influences like asynchronous and nodal libration contributing to its reliability, its orbit can still behave unpredictably. A seemingly insignificant adjustment in Pluto's initial location or speed can set it on a dramatically different course over millions of years. Even so, Pluto's trajectory remains astonishingly stable across immense time frames, extending billions of years into the future. This indicates that beneath its seemingly erratic path, Pluto's journey around the Sun operates within an underlying order. When it comes to forecasting events involving planets with irregular orbits like Pluto, the inherent unpredictability makes long-range predictions difficult. Sophisticated models help scientists estimate future orbital paths, but they also expose the limits of what we can predict with confidence. These models are heavily reliant on exact initial data and the ability to simulate complex interactions. Even the slightest miscalculation can yield vastly different predictions, making precision forecasts challenging. The inherently chaotic nature of orbits like Pluto's reminds us of the ever-shifting nature of the universe. Although we've made strides in understanding celestial mechanics, Pluto's situation underscores how much more remains unknown. The vast distances between stars and planets make frequent collisions rare, and rogue planets, those not bound to any star, are uncommon compared to the sheer number of stars and regularly orbiting planets, making direct planetary collisions exceedingly unlikely. Investigating how the gas giants influence Pluto's orbit helps illuminate the broader dynamics of our solar system. Each planet's mass and location subtly alters the motions of other celestial bodies. Still, despite all these complex gravitational interactions, some top-tier scientists continue to warn about a possible Pluto-Neptune impact. This raises the question, why are these worries gaining traction now, despite the overwhelming number of stabilizing factors? Neil deGrasse Tyson, a widely known astrophysicist, brings a distinctive perspective to the mysteries of our solar system, particularly concerning Pluto. Tyson, who famously supported the reclassification of Pluto as a dwarf planet rather than a full-fledged one, offers thoughtful reflections on how our grasp of orbital dynamics is always expanding. To him, Pluto's change in status isn't a demotion but a reflection of the evolving nature of astronomical knowledge and classification. His approach emphasizes constant education and adaptation. Tyson views the complexity of Pluto's orbit as a compelling sign of how much we have yet to uncover. He believes these unresolved mysteries are precisely what makes space exploration so captivating. Tyson also recognizes the role that high-profile cosmic events play in stimulating public fascination with astronomy. He sees occasions like Pluto's orbital peculiarities and its planetary redefinition as opportunities to engage the public's imagination and inspire deeper interest in the cosmos. By highlighting the dramatic and sometimes bizarre aspects of orbital physics, Tyson hopes to foster broader appreciation and understanding of space science beyond academic circles. Tyson continues to caution the public about the possible perils linked to Pluto's unpredictable movement. Following extensive research, he has expressed concern that the three-body problem might present an actual hazard, suggesting a long-overdue collision with Neptune. He further emphasizes that such an event could potentially disrupt the gravitational harmony of the solar system, leading to catastrophic consequences that might even extend to Earth. A collision of this magnitude would be unprecedented, unleashing vast quantities of energy and potentially shattering Pluto due to its relatively small size and icy makeup. Debris from the crash could spread across the solar system, posing potential risks to other planets and their natural satellites. For Neptune, depending on the details of the impact, the collision might even alter its orbit or atmospheric properties. Michio Kaku, a renowned theoretical physicist known for his work in string theory and popular science communication, also provides valuable insight into this scenario. Kaku's perspective links the study of planetary motion to broader questions in fundamental physics. He views Pluto's orbit as a window into the future of space exploration and believes that understanding the gravitational interplay between celestial bodies like Pluto and Neptune offers crucial knowledge for planning future missions. This understanding could improve how we navigate through the outer reaches of the solar system and anticipate potential threats. Kaku also stresses that the lessons derived from Pluto's orbit are applicable to the study of other celestial objects, offering a structural framework for reaching and analyzing distant regions of the cosmos. In discussing planetary physics, Kaku often underscores the profound relationship between orbital mechanics and theoretical physics. He believes that the complex gravitational interactions, such as the delicate dance between Pluto and Neptune, are manifestations of the universe's fundamental laws. Kaku's research, particularly in string theory, aims to explain these underlying principles. He proposes that exploring the dynamics of planetary orbits, especially those as intricate as Pluto's, can reveal deeper truths about the structure of reality. Like Tyson, Kaku has also speculated about the consequences of a Pluto-Neptune collision. From his theoretical standpoint, such an event would be a significant milestone in observational astronomy, potentially contributing to the advancement of string theory. String theory, which envisions particles not as points but as tiny vibrating strings, attempts to unify all forces and matter in the universe. A massive impact in the outer solar system could produce conditions of extreme gravity and energy, offering a rare opportunity to observe how matter and forces behave under those circumstances, a critical area for string theory. The gravitational waves released by the impact could provide valuable data for testing predictions related to gravity and spacetime as modeled by string theory. Although Earth would likely remain unaffected physically due to its distance from the impact zone, the scientific implications of such a cosmic event could be profound, potentially enhancing our understanding of fundamental forces and matter. Pluto's orbit serves as a remarkable demonstration of celestial dynamics, showcasing both stability and chaos in our solar system. Its unique path, influenced by the gravitational pull of nearby giant planets, especially Neptune, highlights the elaborate and fluid structure of space. The universe holds countless mysteries, and the three-body problem is just one among them. Other possible disasters loom in the minds of scientists. While the probability of planetary collisions remains low, it is not entirely impossible. The manner in which planetary orbits are altered by various forces, particularly gravity, is epitomized by the three-body issue. In tightly packed systems like TRAPPIST-1, which houses 7 Earth-sized planets, gravitational interactions can produce rhythmic orbital resonances. Over time, these resonances may destabilize orbits, eventually leading to potential collisions. Although TRAPPIST-1 is currently stable, astronomers vigilantly track its planets to study how closely spaced celestial bodies interact, especially under gravitational stress. This research enhances our broader understanding of orbital evolution. Rogue planets, drifting aimlessly through space having been ejected from their star systems due to gravitational upheaval or nearby stellar intrusions, introduce another layer of unpredictability. These planetary nomads can traverse enormous stretches of interstellar space, possibly reaching regions far removed from their original systems. As they wander, there is a remote chance they may encounter and even intersect other star systems. If a rogue planet enters a new solar system, there's a minute possibility it could collide with one of that system's planets. However, given the immense emptiness of space, the chances of such a direct impact remain extraordinarily low.